screen. Okay. Let's continue to one with the what we call chain rule.
Sir?
Yes.
I have a question over there. It's
Sure.
minus 10 divided by 27, but why the result is minus 2.7?
Oh, sorry.
Yeah, it's supposed like minus 37 divided by 10.
Yep.
Right? Yeah, okay. Just checking it out.
Just leave it like that. All right, so let's do what you call a chain rule. Okay, so it's called chain, well, for the reason that we will see. The thing is, if you have a compositions, the composite functions, and what's supposed to be the derivative? We want to find derivative of this. Right, so we'll probably give that little O thing. Okay. Now we need this one to let's see, to be able to make things more complicate things. Okay, compute this one first. Example. Okay, how if we compute this one here? Take derivative of, say, just 2x plus 1 square. Okay. Well, there are a couple of things to do. You can either do this, take derivative of, you square this first. So 224x plus 1. And take derivative from here. Okay. What if you have cube? Well, you can do this. Of course, you can compute the cube first. Cube first, then you get let's see, square of this, 3 times 4x squared plus 3 times 3 times 2x plus 1. Okay, so just expansion of a cube. Again, and then you get 24x squared plus this is 12, 24x. This is 6x. 6. Okay. It becomes more tedious if you compute this one, for example. Not something that it's not something that what you call difficult, but it's tedious. Okay. Or you can compute, what about power 113, for example. Again, this is something that we can do that, but it will take time because it have to expand this power 10, power 113, right? Okay, so we'll try to find if there is a way to compute this easier. Okay. All right, so what we would like to do here, for example, if you have something like this, and then we would like to write with y equals 2x plus 1. Okay, so this becomes a compositions. As uh, as compositions. All right. Remember in the beginning, so how to compute compositions, but what we would like to do here is the decompositions. That is to write down the expression as a using simpler expressions. All right. Okay, if you have a compute this number kind of number with this power, what you would like to do here is compute 2x plus 1 first. Okay. So this is the first one. And then f is raising to some power. Okay. So this is what we have. So we write this down as a, after this becomes take derivative of g first, followed by f. Okay, so this is how we need the rule to compute derivative of a compositions. Okay, so I'll just give you directly the chain rule. Is that G is the differentiable at x equals a. F is differentiable at G of a. This is chain rule. The x of f followed G compute at the number a is this one here. Take derivative computed at G of a, but then you multiply by derivative of G computed at a. That's what we call a chain rule. Okay, so using this using the chain rule, remember 2x plus 1. Okay, so this is the, say, we rewrite this one. Okay. With G is just 2x plus 1. F is raising power 113. Okay, according to chain rule, is that it's its derivative. All right, so from here, compute derivative. G prime is just 2. F prime is 113, x to the power of 112. Okay, so what we have is that f prime. Okay, so this one, but computed at the g of a and g of x. Okay. So what we have is this 113. Replace x by 2x plus 1 power this. Okay. Multiply by derivative of g. Derivative of g is 2. Okay, so you have 2, 2, 6. Okay, so this really helps us in computing this kind of tedious thing, for example. Okay, so this is called chain rule. So why is this called chain rule? Because well, if you have to take derivative of composition of 3, for example, it's getting more complicated. Okay, so you need 3 rules to compute these functions. Okay. What you do here is that take derivative of the outside first, so the f, but compute it at g here. Okay, and then multiply by derivative of what's inside. Derivative of this, again, this is chain rule. Okay, but compute it at h of x. Okay, times okay, so like you're going from outside, so f prime computed at this, g prime computed at this, h prime. Okay, so you can go on and on making this chain, like chain, f1, f2, f3, dot, 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 f, and x, for example. Okay, like a chain. And what you have is f1 prime times f2 primes until f, the last one. Yeah. Chain. Okay. But before we proceed, let's do some derivative of trig first, trigonometric functions. And we would have some much more, many more examples after this. Of trig functions. Okay, so the question is, let's compute this one. Well, if we are able to compute this one, then we know how to compute tangent, derivative of tangent, because tangent is just sine over cosine. Okay, so let's see this one. Is this one. Okay, and just to rewrite the limit later, just compute this one. This is sine of sum. So remember, sine x cosine h. Subtract sine h cosine x. Okay, and then subtract sine x. Okay. Now, what we have here is that let's do some factorizations as much as possible. So what we can do here is that we cannot combine this first and second terms, but we can combine this one here, first and the third, and you can take the sign out. Okay, so sine x cosine h minus 1. And what's left here is that sine h. Okay, and now we write this as, and remember this one. Okay, and let's see. Oh, sorry. What's wrong is this one. This is plus. So this is plus here. Okay. So what we had here is that's cosine and okay. And then take limit. Okay. But recall this is a special form of trig functions, trig limits. This is also special trig limits. Okay. So this one goes to 1. Sorry, goes to 0. This one goes to 1. Okay. So at the end, you have this. This is the first one disappears, and then second one just cosine. Well, if you compute this, just an exercise for you, you get negative sign. Okay, compute this. Okay. Then we can compute. Tan is just sine over cosine. Okay, and this gives you, all right, so derivative of sine become cosine. Okay, times this cosine denominator, subtract sine times derivative of cosine, so negative sine, over the square of this cosine. Okay, so you have this is cosine square minus sine square over, and there's a couple of ways to express this one. For example, you can just directly divide by cosine square, so you get 1 minus, what is this? Sine over cosine. Okay, again, you get the tan square. Okay, but we also know, let's see. Wrong. Minus become plus. Okay. So one way to express this is just divide by cosine square, so just 1 plus Okay. Another is because we cosine square plus 1 is just 1, right? 1 over cosine square, that is secant. So square is secant square. Because for a function, there's only one derivative. So this should be the same. So you have an extra thing here is that you get this formula. So secant square is just a tan square plus 1. The derivative. All right, so you can find the derivative of cotangent of x, derivative of secant, derivative of cosecant. Sorry. Okay. All right. So now we can combine this using all these derivative rules for derivative. All right. So, for example, derivative of sine 5x, for example. Okay. And sorry. And you have to think this as a composition, so decompose. So meaning how you compute sine 5x. First compute 5x and then compute sine. Okay. So by chain rule. Right, so let's write this in the with a key is 5 and f is the sine. Okay, so the outside is just f. Derivative of f, sine become cosine, but computed at 5x. Okay, then you multiply derivative of 5x. This is 5. So this is what you get. Okay, and that's second. Derivative of, say, tangent square x. Okay. Oh, not square, because the square we know how to do square. Tangent 5x power of 5. All right, so think this as, again, compute g. G here is a tangent. And then f as a power of 5. Okay. So then what you have is that f prime, so derivative of power of 5, g. Next, to the 4. Sorry. Okay. And then you got to multiply by derivative of tangent. Derivative of tangent is, yes. So we compute derivative of tangent is secant square. Then we know that this is 5 secant square x. Okay. Another example. Let's do some more complicated thing. Yes. Okay, so it's combinations. You got to use a chain rule to compute this one, and you got to use quotient rule. Okay, so let's compute this one step by step. So derivative of, so this remain like this, derivative of sine times the derivative of sine x squared. Okay, and then subtract by c. I should write this as derivative of this. So 3x squared times sine of x squared x plus 1. This match to the, and you subtract by, there we go. Just remain to compute this derivative. Right? So what you have is, now here comes the chain rule. Okay, so what you have is, there, by chain rule, the sine become cosine. So, but the angle remains the same. This is the angle. The times the derivative of the, say, the angle. So just 2x minus 5. Okay. Then sine of x squared plus, sorry, minus 5x plus 1. Okay. So just keep it like this one. No need to simplify. Okay, so this is what's called chain rule. Any questions?
Sir, I have a question.
Uh-huh.
For the derivative of 10x, which one is more commonly used? 1 plus 10 squared x or secant square x?
Commonly, more common is the secant square.
Okay, thank you, sir.
Uh-huh. The thing with this is that we have a formula comes from the derivative. Okay.
Sir.
Mhm.
So is number 3 is a combination of chain rule and quotient rule?
Uh-huh.
Okay.
Right.
Thank you, sir.
So now after this, the rules over derivative and chain rules, we have quite a large library how to compute derivative. Okay, so let's pick some example from the tutorial. All right, so let's take pick this one up here. For example, this G. Let me G. Okay, so let's we need to compute this one. Okay. Compute it at x equals. All right. So compute this one and plug in x equals 2. Okay. So this is also a combination of product rule, and derivative of g square is that, well, use the chain rule. This is quotient. Okay, so let's compute this. So how to compute this? First, we have a quotient rule. Right? So derivative of the top. So dx of g square, sorry, times f. Sorry, this is subtract f prime. Let's see, okay, g square prime. Okay, defines by f square. Okay, so let's compute this one. Derivative of g square. Well, that is 2g. 2g of, okay, that, oh, sorry, I should say power 2 reduced by 1 become power 1 multiplied by derivative. Okay. F. Okay, so the data here is that, let's see, we need to x equals 2. So what we have is 2g prime of 2, g prime of 2, f of 2 minus g square of 2 . Okay, g square of there. Okay, so let's find out the data. Well, what's the data? Sorry. F of 2 is 5. Sorry, let me write down this one here. F prime of 2 is 3. G2 is minus 4. G prime of 2 is 6. Okay, so let's find this out. So 2 times G2 is negative 4. G prime of 2 is 6. F of 2 is 5. G square of 2. G square square. F prime of 2, so 3. F2, 5 squared. Okay, so this given given. Okay. So compute that. Compute derivatives. Okay, what else? Let's see. Okay. All right, for example, here. This one, for example. See. Find the equation for tangent lines to this graph of function here. 1 plus 2x at the point P 5/4 3. Okay. And P okay, so let's find this out. Problem 4. Okay. Compute the equation for tangent line. Of y equals, let's see, 1 plus 2 tangent x at P pi 4. Okay. So then that's the, we need to find the slope first. So this is our f of x. So this slope is f prime at computed. Okay, so what we have here is that, right, derivative of this 2 tangent just 2 secant square of x computed at pi over 3. Plug in pi over 3. So this is 2 over cosine pi over 3 square. Cosine pi over 3 is, let's see, like this. And the thing is, this is 1, this is 2. Right, so this is triangle. So this one here is 4 square root of 3. Okay, so the cosine is 1/2 square root of 3. Okay, so 3/4. Okay. So 2, 3. Oh, sorry. How is this? 2 times 4/3. So 8. 8/3. So that's the slope. So the equation of the line is tangent line. Is y minus this 3, 8/3, x minus 1. Oh, sorry, made mistake. Pi over 4, this is not, sorry. Okay, so then pi over 4, this is, okay, so this pi over 4, so 45 degrees. So square root 2 over 2. Okay, so 1/2. There. Okay. All right, and let's see. Last thing here is that what we call the, let's see, the higher order derivative. Okay, so for example, if you, what does it mean? This is taking derivative over and over. So keep repeating derivatives. Okay, so for example, just give you an example. What we call a second derivative, if you given a functions, so derivative, or we call it now the first derivative, is f prime or df over dx. Okay, and let's see. Now, if we take second derivative, what's that thing? That is first derivative, take derivative. So this ddx of the f prime. So that's second derivative. What is third derivative? Okay, so this ddx of the second derivative. Okay, and on, goes on and on. Okay, so just give you example here. Let's start with the, say, That's 5x squared minus 7. Okay. Find all derivative. Meaning that find derivative of all order. Okay, so compute this. First derivative, that's easy. Plus 10. Sorry, this is kind of error. Uh, 10x, yes. Second derivative is that's 12x squared plus 10. Okay. Third derivative is, let's see, it's 24x. This derivative is 0. All right. Now it's getting tedious if you write this with this a comma thing. So for fourth derivative, we write this one. Okay. So for 1, 2, 3, 4, for example, this thing as this one. Write this 4, but inside a parentheses. Otherwise, we meant it as a power. Okay. Let's compute. This is 24. Okay. And the fifth, well, derivative of 24, that's 0. And once you get to 0, okay, this remains 0. So that's true for k starting from 5, 6, 7, and so on. Okay, so this gives you all derivative of all derivative of f. Okay, one more thing is that same questions, find all derivative of sine 2x. Okay, so f of x is sine 2x. F prime x derivative. So we use chain rule. We compute this 2x first, right? So you get derivative of sine become cosine. The angle remains same, but multiply by the derivative of the angle here. So just 2. Okay. Derivative of second derivative. Cosine become negative sine. Angle same, but 2 multiplied by another 2. So 2 squared. Third, sine become cosine again. Same angle. But, oh, minus sign, because minus becomes minus also. But another 2, so become over 3. Okay. Power 4. Power 4 is that cosine becomes sine. Or become negative. Let's cancel this negative. Okay. Negative, but you have power 4. Okay. So what is this? This is nothing but, there you go. So if you require to compute the fifth derivative, That's the same as derivative of say again, other 2 sine become cosine and becomes 2 to the 5th cosine 2x. And the thing here, it becomes, the difference with this is just this power. So can you guess what what derivative is? Okay. Okay. This one is, so this zeroth derivative. So the function is considered the zeroth of the derivative. Okay. So you see, this will give you 2, 1. Okay. So for that, it becomes 2k cosine 2x, depending on the k, and then it becomes cosine becomes sine dash. I hate this one. Almost the end, and then it's stuck. Sorry. Cosine sine, and from here you get again negative 2k become cosine, and you can differentiate here. K 0 multiple 4 8, but that's 12. This is k equals 1 5 9 equals 2 6 10 3 let's see 7 11 there. Okay, we'll stop here, and then you'll do the exercise later on with the Kakemal at 2. Attendance open until 9:30. All right, any questions?
No questions, sir.
All right, good. Then we'll stop here then. Stop here.